So now we're into chapter 12. Chapter 12, we only have two sections to cover. And 12.1, we only have one test. But hey, it's a test. I know it's a shocker for you. But we're going to be doing hypothesis testing. I know it's amazing. All right, so what we want to learn is the goodness of fit test. The goodness of fit test is an inferential procedure used to determine whether a frequency distribution follows a specific distribution. All right, so find the null hypotheses for the following. So the M&M company claims that in a bag of plain M&Ms, 13% are brown, 14% yellow, 13% red, 20% orange, 24% blue, and 16% green. But is that accurate? The percentage of the company claims are what we expect, i.e. they make the null hypothesis, see? And then we tear open the bag and we get to observe. So then we have to compare the two. All right, so the null hypothesis is what you expect to have happen, what you think will be in existence unless you can prove it otherwise. I said it before, but it's sort of like playing the game of Clue. Like, if you've never played the board game Clue, I highly recommend it. It's one of my favorites when I was a kid. But I say Colonel Mustard did it in the dining room with a candlestick, and can you prove me wrong? So this little statement right here, this is our Colonel Mustard, right? It's what we say is happening unless you have a card to prove it otherwise, unless you can get some data from a bag of M&Ms to prove it otherwise. All right, so now you think an 8-sided die is fair. 8-sided die, right? There's 8 sides to it. And you expect each side to come up 1/8, right? But is it really? So you're going to roll 1,000 times and observe the actual number rolled. Then we compare the two. So what would be the null hypothesis? What are you assuming to be true? Well, you assume the die is fair, right? So that means the probability of side is 1 is equal to probability of side 2, which is equal to probability of side 3, and so on, which is equal to 1/8. All right, Republican voters have to vote for a candidate in the primary for the U.S. presidency. You can tell when I wrote this question was summertime. Based on polling, we expect that Rick Perry will get 32% of the Republican vote, Mitt Romney will get 41% of the vote, and Ron Paul will get 16% of the vote, and so on. But does what we observe on Election Day match the distribution we expect? So what do we assume? We assume that the probability for Rick Perry is 0.32. The probability for probability proportion for Mitt Romney is 0.41. The probability for Ron Paul was 0.16, and the probability for everybody else was 0.11. Of course, because they have to add up to 100%. This is a primary, so only Republicans would be voting in it. Say. All right, there we go. All right, now medical research body believes that in childbirth, 1% of births will result in stillbirth, 14% of births will result in complications that require neonatal care, and 21% of births will result in complications for the baby that do not require extra care, and the rest will be just fine. So does the hospital have statistics that match those results or not? So we assume that this medical research body knows what they're talking about, and that the stillbirth is 0.01, the neonatal is 0.14, the non-neonatal troubles are 0.21, and everybody fine is 0.64. That's what we assume to be true, so that's our null hypothesis unless we can prove it otherwise. Now, how is this different than what we were working with before? Well, if you remember chapter 9 and 10, we were only working with one thing. So it'd be like the proportion that are neonatal in need of neonatal care. That's it. So we would just deal with the 0.14 and lump all the rest of them together in something else. And then in chapter 11, we dealt with, hey, what's neonatal versus non-neonatal? Like, how do we compare those two and ignore the rest? That kind of thing. So two populations, if you will. Or like, what's the neonatal care for female babies versus male babies, or something like that. Right? That would have been chapter 11. But now for chapter 12, it's really talking about a whole bunch of proportions all at the same time, which we've never had before in our null hypothesis. But we have it now in chapter 12. You'd think it makes chapter 12 harder, but not really. It's more the same. You'll see. All right, now before we can get into it, we have to know how to find expected counts, because what you're trying to do is compare what really happens with what you expected to have happen. In chapters 9 and 10 and 11, that's a little bit easier because you just have to find the z-score or whatever for the classical method and say, I was 4 standard deviations away, reject the null, that kind of thing. But now we're going to have to find something a little bit more complicated. It's not enough just to find our z-score. We have to figure out what we expected to have happen in each category. So there are 12 astrological signs that divide up the calendar year equally: Gemini, Taurus, Libra, etc. If you were to look at a distribution of 1,067 people, compute the number you would expect to be born under each sign. So the astrological signs divide up the year, right? What do you expect? And according to this up here, what you do is you take the probability of observing the first outcome and you multiply it by how many there are, and that'll be what you expect. So for example, the probability of Gemini, for the hell of it, because that's my sign, is 1 out of 12, right? 0.08333333. So then what's your expected number? It's n, which is right here, 1067, times p, which was 0.083. Or if you like here, you can say it's n times 1 over 12, right? Because it divides the year up evenly into 12 pieces. So there you go. Your expected number is 88.916, repeating. And of course, there's nothing really special about about Gemini. So, I mean, they all kind of work this way, right? They would all be equal, right? If the astrological signs divide, the birth rates up evenly, the births up evenly, the birth months up evenly, then therefore every sign should happen an even number of times, more or less, right? In other words, we assume it's basically a uniform distribution. Won't always be that way. Like if you were doing, oh, I don't know, this M&M one here, the orange ones should happen more often than the green ones, say, or something like that. But this particular one, because the astrological signs divide up, everybody see that word, equally, yeah? That's why each one of these is the same. Right? If it wasn't equal, then they wouldn't be the same. All right, so then how do you test these goodness of fit things? Well, it's a chi-square distribution, and the chi-square statistic is this guy. The observed minus the expected, you square it and divide it by the expected. Luckily for you, computers can do most of this stuff. And hey, look, it's a hypothesis test. Shocking, isn't it? Look, it's got 6 steps and everything. I know, it's like you've never seen one before. All right, so let's look at one that's pre-done for us. As a matter of fact, we're going to do it in Excel. Hold on, let me bring up an Excel spreadsheet. All right, it's going to be a little strange. We're going to get our data out of this here. We said the expected. Oh, we better put the sign. All right. Hold on, let me copy these in. We need our sign and our expected number. And I'm going to give you a hint. We don't even need that, but we'll figure that out in a second. All right, so we've got our astrological sign and our expected number. And if you like, it might even be a smart move to have Excel calculate all this for us. We'd done it before, I know, but you just take 1 divided by, equals 1 divided by 12 times 1067. There we go. Now I've got all the decimal places in all their glory. And there we go. Okay, so that's the expected number. Now the observed is what actually happened. So, oops, except you have to spell it correctly. Observed. There we go. All right, now I know it doesn't seem like I gave it to you, but I actually did. It's in the Minitab output. Minitab gives it right here. So they found these numbers of actual, this was the 1,067 richest people in Britain, 1,067 richest people in Britain. And so you can see more of them are Geminis than Pisces. Only 73 of them were Pisces, 110 of them were Geminis, and so on. So I'm going to type those numbers in. So 110, 104. Okay, there we go. So this is what we actually observed in real life. I'm going to put this all in a border and everything's going to be great. Cool. All right, so now how do we run the test? Obviously, you're not going to get this Minitab output, but how do I get chi-square out of StatCrunch? As you can see, I can. So let me go to StatCrunch. Oops, here it is. I don't know what that is, but I'll delete it. There we go. Okay, so I'm going to take this lovely data in here. And honestly, I really only need the observed, but that's all right. I'll put observed right here. At least I think I do. Maybe I need the expected too. You know what? Let me take the whole thing, just for the fun of it. So I'm going to copy. Hopefully you can see that. But I'm just selecting all of that table with the observed and the expected and stuff. And then I'm going to paste it in. There we go. Ooh, and I'm going to make this larger. Hold on one second. Edit, fonts, just so you guys can see it, because otherwise it's so blasted small. There we go. Okay, so now I go to stat. Actually, let me also make these wider so you can see. All right, stat. And let's see, goodness of fit. Look at that right there. Chi-square test. Your observed is in, oh, we did need them all. Your observed is in the observed column. Your expected is in the expected number column. And you click calculate. And there it is. Let's see if it matched. Copy. Go in here. Paste. There it is. Exactly. 2.2575. That's as easy as it is. So the observed, of course, you have to be given. You wouldn't know that ahead of time, but you were. And then the other part, the expected part, comes from this, right? We had to find it. And I found it with Excel right here. And you should too for your technology assignment if you're following along. If you're one of my online students. And so there we go. And we can see the p-value and the chi-square statistic right there. And of course, we all know that that p-value is not nearly small enough to be rejecting, right? We only reject the null hypothesis if we have a small p-value. So the Minitab output contains a large table, right? See the table in this? This is Minitab, always helpful. So it gives you the observed values, nice. It gives you the expected values, right? That's over here on the right. It gives you the test proportion, which is 1/12, which is 0.08333333. That's why it's giving you that. It gives you all sorts of good stuff. And it gives you the category name, I suppose. Cool. All right, now the null and alternative hypotheses. The null hypothesis is that every sign, I didn't want to write them out, but Gemini, Taurus, and so on, they're all 1/12 of all the wealthy people. So this is all the wealthy people in Britain. So it's saying every sign has about 1/12 of the wealthy people. Okay, and then the alternative is that they're not all equal to 1/12. That, hey, Gemini is bigger, maybe more people are, born Geminis or something. Maybe if you're Gemini, you're more likely to be wealthy. Who knows? All right, so what are the degrees of freedom? That's 11 because there were 12 signs here, 12 categories. 12 minus 1 is 11. The test statistic was 13.57. You can see it right there in green. The p-value is 0.257. It's circled right there in red. All right, so then we would draw a chi-square curve. Remember, that's skewed right. Don't make a normal curve. Make a skewed right curve. You put 13.57 down on it, kind of vaguely where you think it is over on the right. And then you shade all of this, and you should be shading a lot because that's a large p-value. It's 0.25. It's literally a quarter of the curve should be shaded. That is not nearly low enough to reject, so we would not reject the null hypothesis because 0.257 is much greater than alpha. So we would not reject the null, which means this is not a significant result. So I know it seems like Geminis are more likely to be wealthy, but the difference between Gemini and Pisces, even though it's 110 to 73, we just proved that it's not that significant. And that's what we would say here. There's not enough evidence to support the claim that the distribution of astrological signs is not even amongst the wealthy. Okay. So I know I never read the question to you, but what we were trying to argue here is like, oh, if you looked at this table, you'd think, oh, that's just crazy. If you're a Gemini, you're way more likely to be wealthy. Oh, But we just proved mathematically that that's not the case. That, quite frankly, that kind of distribution from 110 to 73 has a 25.7% chance of happening. It's not rare. This is not, they're not vastly apart. If Pisces was at 3, then we'd be talking. But Pisces is at 73, and that's just not enough difference between the two. And that's what this is showing here. That this distribution, all these different numbers, are not far enough away from being equal, not far enough away from being 88. They're all hovering around 88. Some are higher, some are lower, but it's all still around 88. You've got a p-value of 0.25. That's not low. You do not reject. You don't have enough evidence to support the claim that the astrological signs are different for wealthy people. All right, we're done with 12.1. I know it was quick, but it's over. All right, I'll meet you back here for 12.2.